Hi, so I want to convince you that the alphabet actually really matters here. So commonly when we give you problems to solve, the alphabet really technically doesn't matter, but here in this case it actually does. So here I have two languages which are exactly the same except the alphabet's different. So here we have the 0 and 1, and we want the number of 0 1s in that string W to be the number of 1 0s. And the second one is all strings with 0s, 1s, and 2s. So I want to convince you that L1 is regular and L2 is not regular, which really shows that there really is a difference between the languages here. So if you look up a theorem on one of my papers I published, you can actually find out or understand this condition really quickly because we gave a sufficient characterization for this, but I want to actually prove this directly. So we can actually phrase the first one, L1. Let's try that one first. So if the number of 0 1s equals the number of 1 0s, I claim that that corresponds to all strings that start and end with the same character. So why is that the case? So let's say we see a 0 1 somewhere. Then if the number of 0 1s equals the number of 1 0s, we must see a 1 0 at some point because it's got to match with this one. So let's say it appears after. If it appears before, the argument is exactly the same. So, and then we have stuff appearing before and after. We don't know necessarily what. Well, the key here is that in this region right here, we must have the same number of 1 0s and 0 1s. So the number of 0 1s equals the number of 1 0s. And the reason is that there's no other character that can go here. So it's either the case that it's just a big span of 1s right here, because I said it in that particular case it doesn't change characters, or if it does change character, it can only change from a 1 to a 0, because that's the only other character. And then the 0 must eventually change back into a 1, and inductively, you can actually show that we will get exactly the same number on the inside. So if you expand that out all the way to the ends of the string, it's not possible, for example, for a string to start with a 0 and end with a 1, because that means that the number of times it switched between the 0 and the 1 is odd, which means that the 0 1 count is one more at least than the 1 0 count. So that I claim that L1 then is the set of all strings that start and end with the same character. So we can actually make a DFA for this really quickly. Is if it starts with a 0, it's got to end with the 0. And if it starts with a 1, it's got to end with the 1. So here, this is a pretty common machine. This one I'm going to make a final state because the empty string starts and ends with the same character, namely none of them. I mean, you could make it not a final state if you didn't want to. So I should make this state final too, because if I just read a 0, then I have started and ended with the same character. And if I read more 0s, I should stay here. If I read a 1, I should go away into a different state, because at this point I started with the 0 and currently I've ended with a 1. If I read more 1s, I should stay over here. And then if I see a 0, the counts are back in unison, and so we can come back to Q1. And then the states down here are going to be very close, very similar, I should say. So it's just going to be flip-flopping what the 1 and the 0 do here. So the 0 is going to stay over in Q4, and the 1s are going to come back to Q3. Okay, so this is a DFA for L1, which shows that it's regular. So now I want to convince you that L2 is not regular. And the key idea is to use these 2's. So the 2's are, if we try to separate the 2's away from every occurrence of 1 0 1 from the occurrences of 1 0, then we can put a bunch of 0 1s at the beginning and a bunch of 1 0s at the end. And if we pump within the 0 1 piece, then I will never touch the 1, 0 piece because the 2's are separating all of them. So what we're going to do is we're going to use the pumping lemma, although there are other ways you can prove this too. So how we're going to do it is we're going to pick the string, and I'm not going to go through the whole argument here. I assume that you've watched the pumping lemma videos. You've watched them, right? Okay, good. So we're going to pick W to be this string. So 0, 1, 2 to the P, and then 2, oh no, I have it backwards. 1, 0, 2 to the P. So what does this look like? It looks like 0, 1, 2, 0, 1, 2, just repeating this over and over, 0, 1, 2, and then it's going to eventually switch to this segment here. So we're going to get 1, 0, 2. Maybe I should use that in a different color. So let's use green. So we're going to have 1, 0, 2, 1, 0, 2, etc., 1, 0, 2. Okay, so I claim that this is this is a good string to pick. Why? Because the pump piece must live in this segment right here, so the number of 1 zeros will never change. But I'll try to change the number of 0 1s. So what can we do here? Well, let's see. So we actually have to handle different cases here. So if the y contains a 2 at all, if the y part contains a 2, then if I just eliminated that 2 right there, then, or actually if it's equal to 2, then what happens is I created a 1, 0 instance right here. So that's actually pretty interesting. So if we have y is equal to just 2, I should say, to just 2, then look at x, y to the 0, z, which is the same thing as xz, which means that one of the 2's is going to be completely removed, which means that the number of 1 zeros went up in total because this side didn't change. This side never gained or lost a 0, 1, but it gained a 1, 0. And so therefore, we're done. And so we'll have a different count of 0 1s and 1 zeros. So the number of 1 zeros went up, namely it went up, and number of 0 1s unchanged. I should put it down. Unchanged. Okay, well, what if it's not just 2? Well, if it's 0 or 1, actually, what we can do is, actually, no, that's fine. So if it's 0 or 1, well, if it's a 0, then I claim we can actually, if we look at 0 or 1, it's exactly the same idea. But let's look at 0. If I delete this 0, it's exactly 1 0 being deleted. Then that means that one of the 0 1s went down in count, but the number of 1 zeros was unchanged. So again, we're going to look at x, y to the power 0, z, but the reasoning is different. So the number of 1 zeros unchanged, and the number of 0 1s went up. Down, I should say. It went down. And it's the same reasoning if you have 0 or 1, if it's exactly 1 0 or exactly 1 1. So it may seem like I'm handling a whole bunch of different cases here, but I claim that this is all we need. So if we have just the 0 1 by itself, do exactly the same thing as before. So if it's exactly just one occurrence of 0 1, delete both of the characters, because that corresponds to deleting an occurrence of y. And so we'll have one of the 0 1s go down, but the number of 1 zeros was unchanged. So again, it's the same reasoning. If y is 1 2, then what can we do here? So actually we can handle the case of 2 0 also. So namely, if y contains a 2. And this also includes 0 1 2, I guess. But we're going to handle that in a second. So if it's one of these ones, then if we if we delete the 1, 2, then what's going to happen is that this 0, 1 is going to be deleted. So that means that the number of 0, 1s went down and the number of 1, 0s was unchanged. If we delete the 2, 0, so maybe this should be a different case. That was my mistake. So 1, 2, so we're going to look at the same one, and the reasoning is exactly the same as before. If y is 2, 0, then we're going to do exactly the same as before if we delete the 2, 0 here. But what's going to happen is that we're going to again create a 1, 0 pair. So the number of 1, 0s went up, but the 0, 1s were unchanged. So here we're going to have the number of 1, 0s went up, the number of 0, 1s unchanged. It's a lot of different cases, but we're going to handle all of the rest of them pretty quickly. So if y is exactly 0, 1, 2 by itself, we could just delete it. So if we pump down, we're going to remove a 0, 1 occurrence, and then we'll get the exact same idea. So here, the number of 1, 0s unchanged, and the number of 0, 1s went down again. And then finally, what we're going to do is we're going to handle a whole bunch of them all at once right here. So if it's 0, 1, 2 to the power alpha, and then let's say a string, let's call it w, where w is in one of these right here, and we must say that alpha is at least 1 for this to actually be different than the other cases, then we can just pump down again. So we're going to get exactly the same conclusion as before. And in fact, there's other cases too, like if y has stuff before and stuff after. So I'm not going to handle every single one of those cases, but you can actually show using the same logic that you can always find a way to pump out of the language. And so therefore, through a long proof right here, we have shown that L2 is not regular. So the thing to keep in mind here is that the alphabet matters, so respect it. So hopefully that was interesting. Leave comments about these two languages in the comments down below, and anything about alphabets in general. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.